Okay, we want to decipher this rational function x squared plus 20x plus 100, all divided by x plus 10, and figure out what it looks like, where the intercepts are, what kind of asymptotes it might have, and anything else about it. Let's start by looking at the function. The numerator has a degree of 2, and the denominator has a degree of 1. Now, if we take the difference of these degrees, 2 minus 1, we get 1. And what that tells us is that this rational function is going to end up looking like something with degree 1, a line. So we should expect this to look like a line, just a linear function. There just might be some interesting things happening. And the way we figure those things out is by seeing if we can do any cancellation. That's the first thing we want to check out. So take the numerator and factor it. You can do factor by grouping, completing the square, magic X, magic diamond, whatever it may be, but you're going to get x plus 10 in the numerator times x plus 10. And in the denominator, we also have x plus 10. And if we notice, we've got x plus 10 that can cancel. So what we have is x plus 10 as a simplified f of x, meaning that the original function is going to look like the line x plus 10, a line with slope 1 and y-intercept 10. There's just going to be a key difference, and that difference is coming from the cancellation that we saw before. X plus 10 is where the cancellation is happening. We want to check where that equals 0. Subtract 10 from both sides, get x equals negative 10. Since you were able to cancel in the original function, we have a removable discontinuity, aka a hole. And we've just discovered that hole happens at an x value of negative 10. Now, we can plug that negative 10 into our simplified function. So that's f of negative 10 equals negative 10 plus 10, which gives us 0. So we have a hole at negative 10, comma 0. So that's an interesting thing we want to hold on to. So the original function is going to look just like x plus 10, except for the hole at negative 10, 0. On to step 2, x-intercepts. Well, we can see from here, from the hole, that the y value is 0 at x equals negative 10. So for x plus 10, there's an x-intercept at negative 10. However, the original function is undefined at negative 10, ergo, why we have a hole. So what that means is that holes override x-intercepts. And if it was at the y-intercept, it would also override our y-intercept. So the holes, whatever happens to the original function, overrides what may be happening in the reduced function. Even if you have an intercept, it might not exist if it's undefined for the original. So we have no x-intercept. For the y-intercept, however, we can just plug 0 into our simplified equation. That's 0 plus 10, which is 10. So we have an intercept for y at 0, comma 10. So there we go. We have some more interesting pieces. Now let's look at the vertical asymptote. As you can see from our simplified function, we no longer have any factors in the denominator. So no factors in denominator, which means there is no vertical asymptote. So not any. Then we look at horizontal asymptotes. Well, we can use the acronym BOTN. And that is bigger on top none. What that tells us is if the original function has a degree on the top bigger than the bottom, we are not going to have a horizontal asymptote. So we can say also not any. So we have no asymptotes for this situation. Now it wants us to graph that. If I had a vertical or horizontal asymptote, I might start there by doing dashed lines at x equals whatever the vertical asymptote is and y equals whatever the horizontal asymptote is, but I don't have that. So I'll go ahead and graph my hole at negative 10, 0. So that's right there. And my intercepts, there isn't an x-intercept, but there is a y-intercept at 0, 10. So that's a filled in there. And then we can just connect them. This will look a lot better for you on paper than it is for me here. But we're looking at a line something like that. So this is f of x equals x plus 10, with the major difference being the original function is undefined right there. So there's a hole. And so that's step 5. Now we just have to quickly look at the domain. Well, everything exists except for at -10 we have hole. So in interval notation, we have that the function goes from -infinity to -10, has a hole, so it's not inclusive, union -10 to infinity. This tells us we have everything except for -10. The union is combining these two intervals to show that it's consisting of both of them. Now we might want to write this also in set builder notation, and that looks something like this, where we have x such that, that's what the vertical line means, such that x does not equal -10, which says the same thing. It just means that we have all x's in the real numbers except for x's such that you get -10, or that it equals -10. And that is our domain, and that's our entire function. We've deduced everything from this rational.